And with that being said, Tim, do you want to go ahead and kick us off?
All right. Um, yeah, so I'm here to talk about blind mate quick coupling, specifically for this OCP project, ORV3 blind mate quick connector. All right. There we go. I'm getting the circle. I'm Tim Marquis. I'm the engineering manager from Parker Hannafin. I'm here to present this. I'm presenting on behalf of the quick coupling manufacturers. There are four manufacturers, as Glenn mentioned. Parker, Sane, Safeway, and Eden, all involved with this project. Just a little bit of background. Traditional blind mate couplings, they've been used in this type of application for a significant amount of time, I'd say. And they are typically held together. You typically have a manifold on one side, and then you have maybe the IT gear. It's panel mounted, or it's directly mounted into an IT gear on the other side. And as they mate up, they have to seal. So as the IT gear gets pushed in, both halves get pushed together, and they have to seal up. The typical tolerances for sealing up between two coupling halves, maybe 0.1 meters or something in that range. And as you get to some of the IT gear, obviously trying to line them up within that level is not necessarily something that is practical to do. So typically the male couplings will have a little bit of float built into them. So that way they can float, make up a little bit of the tolerance, and be able to connect up to the other half and reliably seal. Excuse me. The problem in this is that typically you have 1 millimeter of maximum alignment travel and virtually no angular misalignment with some of the traditional couplings that are out there. So how do you make this coupling work for misalignments that account for a full tolerance stack up of a full rack and all these other manufacturing processes? Glenn talked about how they're tightening manufacturing tolerances, or the tight tolerances of the racks or the manifolds. Even at that, there's still much more than what you typically see in a blind mate coupling. So it includes the rack, the manifold, the IT gear, all the plates, the latch mechanisms, and it's in all the dimensions as well. It's both the axial travel, how far it goes in, it's the radial around, and how much angular misalignment in basically any direction you may be able to get to be able to line all these parts up. So then we have to be able to account for all those tolerances and then still maintain or even exceed the current seal reliability. Obviously, we're talking liquid cooling within electronics here, and everybody's always afraid of any kind of leakage or spillage. So in that, you get the increased axial tolerances. Those are making the parts longer, and the longer parts do become more difficult to manufacture and produce. The increased radial flow, to the amount of radial misalignment you have to get, makes the parts much bigger in diameter. And then the angle now requires much more guiding and length, which creates just much more space and much more that you have to deal with to be able to connect these parts up. As you can see, the extent of the travel, it's now, instead of just a slight offset, and especially if I didn't point it out in the previous slide, instead of a slight offset you get on a traditional blind mate, you get a much more exaggerated offset and angle with the new requirements. So in some of these concerns in as well, materials, using stainless steels through our material list for couplings, you can end up with galling concerns, manufacturability concerns, the alignment of the extreme angles, and the seal integrity. So in working through that, the solution that we came up with, it includes, as kind of Glenn showed a little bit, the female coupling is rigidly mounted into a manifold. But the male coupling now it's a single piece through the part, but allowed to float in basically all three dimensions. And then after it disconnects, it centers back to be able to help recenter and reset all of the tolerances, so you don't have to have necessarily as big of a female half. So if it didn't center back to where it was, the female half would have to be even bigger to allow for more gatherability, as Glenn says, or guiding to be able to bring the two halves together. So as I was saying, so when it's fully extended in the full extent of its travel, it can move backwards and then into the extremes of its travel, both radially and at the extremes of the angles. When it's disconnected and the two halves come together, come apart, it will center and then be able to allow when the two halves to come together, there is less variability and less misalignment coming here. The testing that's currently in process, like Glenn mentioned, all four coupling manufacturers have produced product, and we're testing all the float limits, the force limits, how well this is able to center, the connection cycles, all the burst pressure and pressure drop, leakage and spillage. We obviously don't want to have any kind of issues coming out from these parts. And through our initial testing so far, I think everybody can say that the parts, well, it feels like all of the tolerances, and maybe the latch folks might say this as well, but it feels like we've taken all the tolerances of the system and we asked the coupler to take care of as many as possible. And I'm happy to say, quite honestly, with even these exaggerated limits, we are finding ways to make these parts work. When Glenn first asked for these exaggerated radial limits and angular limits, it definitely is a challenge to make everything come together. But as the group has been working together over the last 10 months or so, I think we've been able to find something that actually does work pretty well. Moving forward from that, the advanced cooling solution, the call to action, you get the cold plate work stream and the advanced cooling solution work stream, and definitely get involved going forward. And that's what I had on the couplings.
All right, thanks, Timothy. Any questions for Tim? I do see a question that came from the chat. I'm not sure if it was for you or for Glenn. It's asking for an idea of the pricing on a pair of blind mate as well as a blind mate manifold.
Yeah, I think for pricing, you'll have to contact individual manufacturers, but wouldn't be something that would come from a presentation like this. But I'm sure we'd be able to help you.
Let's give it another minute or two and see if any questions show up. Got a couple folks that are joining the Zoom call here, so we may be getting some live questions.
But you must have done some basic homework. I'm not talking about precise pricing. You know, any engineer, you must be an engineer. Any engineer must have a ballpark idea. Are we talking about $20 a pair? Are we talking $5 a pair?
The Zoom call here, so we may be getting some live
questions. Yeah, in terms of this is a technical presentation. I'm definitely not allowed to get into pricing levels. I don't know if Glenn, you have any comments, but I can't offer anything.
Any engineer,
I agree with what you're saying. Yeah, I mean, this is a technical presentation, and that's what we're going to focus on. Thank you for the question, though.
What's the size of the that opening, or the holder that holds the male part? How big is that that part?
Yeah, this comes out to be about 38 millimeters in a diameter. So this is a 5 millimeter coupler design. The 3 millimeter would end up being a little bit smaller.
Okay, so a 1U server that only had 44 millimeters of usable space inside the sheet metal enclosure could still include one of those and still allow for all the travel and angular.
Right. Yes, that was the intention. It's getting up there in size. The 3 millimeter size will be a little bit smaller as well, to definitely be included in the 1U.
Yeah, I think that idea is the target is the 3 millimeters for the 1U and the 5 millimeters for a 2U and up. Yeah.
But how much fluid flow? How many liters per minute?
I think we'll get into that at a later date. I don't know if we're talking about that right now.
Oh, all
We're-
right.
We're,
Well,
we're still,
'cause-
we're still doing a bunch of our testing, as I mentioned, right?
Okay.
So-
Well, yeah, because what we're seeing is, we're getting up to 3 wide, needing up to 700, almost a kilowatt per server. And so if that pushes us from 3 to 5 millimeters to get to a kilowatt on one loop based on fluid flow, that's an important thing to know.
Thanks for the question, Phil. Definitely encourage you guys to continue this conversation in the chat on the FN Virtual platform. We do have to move on to our next item on the agenda. So thank you so much, Timothy, for your presentation. Up next, we've got Mr. Scott Stammer.